Hello and welcome to my lecture on architecture and programming models for GPUs and coprocessors. Today's the 8th session, so that means we're about a third in. We're currently discussing rendering algorithms and computer graphics. In the previous sessions we discussed the very basic concepts like scan conversion. We discussed transformations, and yesterday we already also talked about surface properties and about the properties of light and about the interplay of those components in order to generate fragments and to generate colors for those fragments. Today we're going to talk about another very important topic in regards to computer graphics, and the topic is mostly about something that is called aliasing. And in order to understand aliasing and in order to understand the sources for aliasing and what we can do about aliasing, we also have to talk a bit about sampling theory. So in this discussion of aliasing and sampling theory is loosely based off of the book by Farr, Jacob, and Humphreys that's called Physically Based Rendering. And this is a book that I can really highly recommend. Like, it's one of the most comprehensive books about physically based computer graphics. And there's a nice chapter on sampling theory, and I really recommend that you look into that book and read about the various topics in that book. And the book is actually available online under this URL here, so please go there and have a look. And what I'm discussing next is loosely based off of one of the chapters that discusses sampling theory. So when we're talking about aliasing, I'll first, very informally introduce what aliasing is. Like, I'll show you a bunch of pictures and give you some intuition, and then we will, when we talk about sampling theory, we will get a formal notion of what aliasing actually is, like how aliasing really comes to being. And we'll first only discuss how aliasing manifests. Like, there are just different sources of aliasing, and therefore a technique that is called anti-aliasing, which basically tries to mitigate the impact of aliasing, is a very important component of the GPU hardware. Like, there are certain design decisions that are really only based off of the fact that there is aliasing in computer graphics. Like, for instance, when we sample textures, this can be a source of aliasing, and only for the reason that textures have a tendency to alias so much. The GPUs internally, and all GPUs internally, don't operate on actual fragments, like when we're on a fragment stage, but they operate on something that is called a fragment quad. On those fragment quads, they actually store derivatives, and with those derivatives we can mitigate aliasing in particular in texture space. And this is an example of where aliasing strongly influences design decisions for GPU architects, and this demonstrates how important aliasing actually is to computer graphics. So just like I said, I will first only demonstrate what aliasing is and how aliasing manifests. Like, on the image that you can see here, you see aliasing in image space, right? And in image space, aliasing often manifests as those jaggy edges, what people call them, right? You have transitions where some pixels are covered by surfaces and other pixels aren't covered by surfaces. And at those transitions, we can see those what people call the jaggy edges, like very hard transitions. So this is one occurrence of aliasing, and then there are other occurrences of aliasing. Like, in fact, on this picture here, you can also nicely see that specular highlights. This is a specular highlight where you can see the reflection of a light source on the surface because the surface is slightly specular, and you can see that the highlight also exhibits those aliasing effects that we can also see at the transitions between surfaces and background. So other sources of aliasing are the textures that we discussed before. And what basically happens here is that we're, depending on perspective, choosing different sampling rates in order to access our texture, right? So regardless of what that means technically, you can see here what type of patterns manifest when we do this, and this is also a pattern that that is due to aliasing in texture space. And you can see the very same thing here. Like, this is actually the very same effect that you can see here, only that the texture is a different type of texture. The texture is actually a 3D texture, right? Like in a very similar fashion to how we store 2D texture images, we can also store a three-dimensional uniform grid with texels, and call that a 3D texture, and then we can have a three-dimensional coordinates into that. And then we somehow sample or map the geometry, the texture to some geometry, and there we also have to deal with aliasing. And this is what we can see here is aliasing from a 3D texture. So now we have an idea of what aliasing looks like, and aliasing actually comes in many disguises. Like there's actually a bunch of different different patterns that manifest on images that in the end turn out to be aliasing, and those are really just the most prominent examples of what aliasing looks like on actual images. And it just so happens that for those examples, such as aliasing in image space and aliasing in texture space, there are very efficient techniques to avoid this type of aliasing, or to at least mitigate it. And those areas are particularly well researched and well understood. Like, this here is a list of sources of aliasing, and it is far from comprehensive. Like we already discussed, aliasing in image space and in texture space. Then there are also other phenomena that are prone to exhibit aliasing, like reflective surfaces and like reflections of surfaces and of 3D objects and mirrors. They are actually quite prone to aliasing. And so are specular highlights from light sources that are shining light directly onto on a highly reflective surface. And also shadows, for instance, tend to expose quite a lot of aliasing, and in particular when there are hard shadows. And then there is also something that's called temporal aliasing. And temporal aliasing basically means that you're rendering two consecutive frames, and the scene is in movement. And I know we assume the scene doesn't move, but for our purposes, there is some movement in the scene, be it just that the camera moves. And therefore, objects that earlier were in a certain region of the screen now move and are in different regions of the screen. And just assuming that we have an object that is so small that it only occupies like a single pixel at most, and when that object moves, it is, depending on how we render the object, it is possible that the object just moves in a way that it sometimes manifests as a single pixel and sometimes completely disappears and then manifests as a single pixel again just because it's so far away. And effects like this are actually due to temporal aliasing, and you already have an intuition for that this has something to do with sampling, and in particular with undersampling. So if we were to place like a bunch of more samples, like maybe if we were to use more pixels, or if we were to devote more individual frames to the animation, that we could maybe mitigate those effects. And therefore, we should discuss sampling, and we should discuss how sampling actually works. And we should, when we discuss sampling, we also have to discuss reconstruction. So we'll now discuss sampling and our reconstruction, and we will discuss how that potentially influences aliasing, or how that potentially leads to aliasing in the first place. So let me provide you with some intuition first before we go into the details. And for that, we're assuming that we're in 1D. Like the concepts that I'm showing you now, they also extend into higher dimensions. Like for instance, when we're dealing with images, we're usually in 2D. And when we have a digital image, this is usually a collection of points that were sampled from a continuous two-dimensional domain. And so the concepts that we're talking about here, they extend to higher dimensions, and in particular to 2D and to 3D, where they are most relevant to us in computer graphics. But we will discuss them in 1D so that I can illustrate them better to you. Like we're assuming we have this continuous function here, f of x, and this continuous function, we are able to evaluate this continuous function at certain points. Like we can, for instance, say, tell me the value of f of x at x equals 1 or at x equals 2 and so forth. So we can do that with the function. But we cannot easily store this function. Like the function is just continuous, and it's a complicated function, and it's just not easy to store an analytic representation of the function somewhere on disk. Or for some reasons it's just not worthwhile to do so. And let us just consider another function, and that function is the so-called Dirac delta function. And the function is just 0 everywhere, except for at x equals 0, where it takes the value 1. So we consider this function, and then based off of this function, we consider another function, this is the so-called Shah function. And the Shah function is a periodic function, and it basically consists of an infinite number of Dirac deltas that are shifted to the right and to the left, that extends to minus and plus infinity. Right? Like this is the Shah function. And in order to sample our function f of x, we perform a multiplication of the original function of the f of x function with the Shah function. Right? And the multiplication will basically set everything to 0 except where those spikes from the Shah function, from the Dirac comb, is what people sometimes call the Shah function, where they are. And there, due to the multiplication, the values of that resulting function are just the values of the function f of x at those discrete positions. And we will refer to those values, like those pairs of x values and y values, we will refer to those as sample points later. So this is the what we just did is the process of sampling a continuous function. Like when we sample a given continuous function, then we do this by multiplication with the Shah function. So, and then we can store those sample points. Like for instance, we can store them in a, if we were in 2D, we would just store them in a 2D image file, like in a PNG file, or like maybe in a raw format, so that we don't lose any precision, or that we can easily retrieve them. And that is, at that point, we don't actually use those sample points. We have a means to store those points and to also retrieve those points, but we cannot, in 2D we would want to display them, and when we're storing an image, we would also like to be able to display that image, and this cannot be done yet in a meaningful way. And in order to display the sample points, the sampled version of the function f of x, we have to reconstruct it. And for that, we consider another type of function, and this type, I will colloquially refer to this type of function as a filter. And for instance, this is a very simple filter here, where the filter has value 0 everywhere, except for the range from -1/2 to +1/2, where the function has a value of 1, right? And in order to reconstruct the original function from our sample positions, that means, like, when we're displaying the function, like, imagine that we're having an image and we're zooming into the image, then we need to be able to fill in those positions where the Dirac comb, where the Shah function didn't sample the function. So we have to provide some meaningful values for what we see here, right? Like, we don't get away with just using the sample points, but we have to somehow fill in those gaps, right? And we fill in those gaps by taking that filter and by performing a convolution of the sample points with the filter. And this gives us another function, a reconstructed function. And in the case of this very simple filter here, we get a step function, right? And there are also other filters out there, like a very commonly used filter. Like this filter here is what people refer to as the box filter, because of the shape of the 1D plot here. People refer to this as the box filter. And then there's another filter that is called the tent filter. And if we were to reconstruct our sample points with this filter, that is, we would perform a convolution of this sampled function with the tent filter. Then we would obtain this reconstruction here, and this is basically a linear interpolation. Like what we're basically doing when we're applying a tent filter, we're reconstructing the original function from the sample points using linear interpolation. And obviously, there's just a multitude of different filters that people that you can use. What people also like commonly do is that they use like, for instance, cubic filters in order to more smoothly reconstruct the function. And here things become more problematic actually, because there's more than a single type of cubic filters. And like, there's just a multitude of different filters with different properties that people use under certain conditions. And I mean, you get an intuition here, like when we take this periodic function, right? And when we decrease the period of that function, right, like we basically increase the size of those gaps here, what we're basically doing is we're undersampling the original function. And that, I mean, intuitively, that makes it harder for us to reconstruct the original function, because we have more gaps where we have to guess what's going on in between. Yeah, and let us just back our intuition with a bit of formalism. Like, we first define the Dirac delta function that I informally introduced earlier, and the Dirac delta function is just defined in terms of its integral, and the integral is just 0 except for at the position x equals 0, where the integral is 1. So, therefore, if we have a continuously differentiable function f of x, and we compute the product of the function f of x with the Dirac delta function, what we obtain is the function value at position 0. So, and from the Dirac delta function, we can define the Shah function, which is also sometimes referred to as a Dirac comb or as an impulse train. And the Shah function is basically just an infinite sum of equidistant delta functions with a period of delta, which determines how far apart the individual spikes of those deltas are. And from that follows that when we multiply the Shah function with a continuously differentiable function, we can from that obtain the function values at the very positions where the spikes of the Shah function are located in. And like, this is what it looks like, and we perform our multiplication, like as we saw before, of the Shah function with the continuously differentiable function, and from that we are able to obtain our sample points. So, and then when we obtained our sample points, what we use is a so-called reconstruction filter. And based on that reconstruction filter, we can actually obtain an estimate for the original function, like this function f dagger that I'm depicting here. And we obtain that by taking the sample points, and the sample points in this case are just the product of the Shah function with the original function, with the original signal, is what you will sometimes hear me saying when I refer to the original function. Like we have this multiplication of the Shah function with the original signal, and then we're using the reconstruction filter to reconstruct an estimate for the continuously differentiable function f of x, and we do so by performing a convolution. And the convolution of the two functions is just defined like this, right? Like the convolution is defined for the indefinite integral of the product of f of x and g of x with regard to this offset tau. And as the function that we're computing the convolution for as one of those functions is basically a discrete function, like the left-hand side here represents our sample points. Therefore, we can just simplify the convolution to a sum. So, and this allows us to replace the convolution with this weighted sum here. Like in the case of the Shah function, those two are, in the case of us multiplying the original continuously differentiable function with the Shah function, those two representations are equivalent. So, and you can already see that there's an issue here with the way that we compute the reconstruction. And the issue here is that we're computing this indefinite sum that goes from minus infinity to plus infinity. And this is, of course, potentially a problem. And this problem can be mitigated if one of those functions is bounded to the left and to the right. For the original function, f of x, I'm generally assuming that the function is not bounded. Like we can make such an assumption, but there's actually not a necessity to make such an assumption, because we usually assume, for practicality, that the filter is bounded. Well, like if you consider, for instance, the box filter, and I earlier showed you a geometric interpretation of the box filter, then we say that the box filter is bounded to both the left and both to the right, as the box filter is defined as being 1 only in this integral between minus 1/2 and between plus 1/2. And so that means that the support of this reconstruction filter is finite. So this is a reconstruction filter that has a finite support, and as the reconstruction filter has a finite support, many, like almost all of the terms from this indefinite sum here will evaluate to 0, and therefore we don't have to account for them. Like because as the function is bounded, we can make an estimate which function values will actually evaluate to 0, and only evaluate the sum for the actual values where the sum isn't 0, which is a finite number. And the same holds true for the tent filter. Like the tent filter is also only defined on that interval from -1 to 1, right? Like the support of this filter is actually wider. The box filter is a 0th order filter. The tent filter is actually a 1st order filter, which kind of makes sense, as we're actually by using linear interpolation here, we're using slopes, and in order to obtain slopes, we have to take 1st order derivatives into account. So this makes the tent filter a 0th order filter, and that also means that the support of the filter needs to be wider, which effectively makes us take more of our neighboring sample values, take more of the neighboring sample values into account when computing the reconstruction, right? Like when we want to reconstruct a point, like here on this line segment, then we basically do this by computing derivatives, and for those derivatives, we just don't only need the value in one sample point for one sample point. We need actually the value that is associated with two sample points. And there are other finite reconstruction filters that are based based on using higher order derivatives, like for instance cubic filters are quite popular and give us a smoother reconstruction than the box or tent filter can give us. So so far we were assuming that the original function was reconstructible, and so far we haven't talked about the properties of this reconstruction. Like, we could already see that the reconstruction is somewhat an approximation, but it's like we didn't actually try to quantify how much of an approximation the reconstruction actually is. And as a matter of fact, there's a certain class of functions that have certain properties, and the function with those properties can be reconstructed exactly from only the sample points, given that we've chosen a certain sampling rate. And those signals or those functions are so-called band-limited functions or band-limited signals, and they're a bit of a theoretical construct because they are not so important for us in computer graphics. Like, most of the signals that we're discussing in computer graphics are not band-limited, but still the theory that is used to derive band-limited functions allows us to understand where aliasing comes from. And a study of those band-limited functions also provides us with a means to find appropriate sampling rates based on frequencies inside the function that we're sampling. And to develop an intuition for what a band-limited signal is, we very briefly have to discuss what a Fourier transform is and what it does. And like, the Fourier transform is actually the topic of for instance, of a computer vision class or of a signal processing class. And I don't want to make this a topic of this lecture here. So I'm really only scratching the surface. And the only thing that is important to know is that there are two things, and the one thing is called the spatial domain, which represents the signal in space and sometimes in time. And then there is another domain, and that domain basically represents the variability of the signal. And there's an operator that allows us to go back and forth between those two domains, and this operator is called the Fourier transform. So this is basically everything that I want to say about the Fourier transform. Like, for instance, for the exam, it's not important to understand those equations, and you don't have to be able to derive or to work with those equations. But it is important to understand that there are those two domains, and the signal is actually representable in both domains. And you can go back and forth with the Fourier transform and with the inverse Fourier transform. And on a very high level, the idea behind a Fourier transform is that you basically can represent each signal as a weighted sum of sine waves. And the very basic intuition that we should have about the Fourier transform is the following. Like, consider this rectangular signal here, and the rectangular signal is defined in the spatial domain. That is, our x-axis is, for instance, something like time, or like a spatial axis, like referring to one dimension of three-dimensional space, for example. And this signal can be represented as a weighted sum of sine waves, and it goes as follows. Like, consider this sine wave, for instance. This is this is a approximation to this rectangular signal, and this sine wave has like a certain amplitude and has a certain offset. So we take that sine wave and then consider this second sine wave here, and this second sine wave happens to have the same offset but has a different amplitude. And then we just compute the sum of those sine waves, and then we can see that this that the sum of those two sine waves like approximates our rectangular signal a bit better. Like, this is like kind of a better approximation to the original rectangular signal. And then we add more sine waves at different frequencies, like this sine wave here. And when we add that to our sum, we find that this sine wave actually approximates the original signal even better, right? And therefore, we can, in the limit, we can represent each signal from the spatial domain as a sum of sine waves. And for our intuition, it is sufficient if we think of the two domains as, on the one hand, as the spatial domain that is described in terms of the in terms of time, or in terms of 1 or 2 or 3-dimensional space. And on the other hand, if we think of the frequency domain as the domain of those sine waves and of their amplitudes and potentially of their offsets. So, and while the mechanics of the Fourier transform aren't so important to us, there are certain identities that follow from the Fourier transform that actually are very important to us, like in order so that we can later make our argument. One consequence of the Fourier transform is that there are functions in the spatial domain, and those spatial domain functions have a frequency domain equivalent. Like, for instance, if we have a constant function in the spatial domain, then the frequency equivalent of that constant function is the Dirac delta function. And if we, for instance, have a box function in the spatial domain, then the equivalent of that is the so-called zinc filter. This is basically just sine of x over x. And the Shah function also has an equivalent in the frequency domain, and the equivalent is just another Shah function, but with an inverted period. And similar to that, there are other functions that have spatial domain representations and that have frequency domain equivalents, but those are the most important ones to our argument. And then there's another important identity to us, and this is the fact that this is a property of the Fourier transform. And the property of the Fourier transform basically tells us that a multiplication in the spatial domain is equivalent to a convolution in the frequency domain. And conversely, this is also true for the other way around. Yeah? Like when we have a multiplication in the frequency domain, this is equivalent to a convolution in the spatial domain. And therefore, there's also an equivalent frequency domain formulation of our sampling function from before. Like when we before computed the multiplication of the Shah function with the continuous input signal, we can now equivalently formulate that as the convolution of the Fourier transform of the input signal with a Shah function and an inverted period. And let us just understand what that means graphically. Graphically, that means that we have our continuous signal, and the signal actually happens to be a band-limited signal, right? And when we compute the convolution of the signal with the Shah function, what this means graphically, like we're in the frequency domain here, graphically that means that all those frequency contributions are just replicated along those spikes of the Shah function. So when we compute the convolution of a band-limited signal of a band-limited function with the Shah function, this results in the signal being replicated, and we obtain an infinitesimal amount of copies. So now we have talked about the left half of the sampling and reconstruction function. So the next thing that we have to take care of is reconstruction, right? And we can already see that there is in the frequency domain that if our signal is band limited and we have all those copies, that there is a reconstruction filter, and a reconstruction filter that we know. And if we multiply our signal with that reconstruction filter, it will be able to exactly reconstruct the original signal. in the frequency domain. And this filter just happens to be a box filter, and the box filter's support is proportional to the sampling rate of the Shah function. So the support of the box filter is 1/2 times delta, to the left and to the right. Our box extends by 1/2 times delta, to the left and to the right. And if the function, if the original signal has those properties that the function is band limited, then we can sample it with a Shah function, and we can exactly reconstruct it by later multiplying it in the frequency domain with the box filter. And so it just so happens that, like we talked about the frequency and spatial domain representations of several functions, and we already know that the Shah function has a frequency domain representation which is another Shah function. And we also know, when we have a box in the frequency domain, that the spatial domain representation of that reconstruction filter is the zinc reconstruction filter. And this is actually a depiction of the zinc reconstruction filter. And as you can see, the zinc reconstruction filter has this issue that's like I'm not fully depicting it. This is not a bounded filter, but this is actually a filter that is defined over an indefinite range. And this is, of course, problematic because we're now exchanging a reconstruction filter in the spatial domain. We are now having to use a reconstruction filter that has an indefinite support. And this is, of course, not realistic, right? Like in reality, we just don't have unbounded functions and unbounded filters because we just cannot compute the integrals with respect to them. So there are two problems with this approach, and this makes this approach a bit theoretical, or like rather theoretical. Like the problems with this approach being that the perfect reconstruction filter happens to have an infinite support in the spatial domain, and we're requiring that the signal must be band limited. And like, what does that mean? Like, for instance, this here is a signal that is not band limited, yeah, and we just so happen to have sampled that signal in the frequency domain, again with another application of the Shah function. And now if we reconstruct this signal using our box filter, and we're in the frequency domain here, what happens is that we obtain this new signal, right? And this is definitely not the original signal. Like, the original signal looked something like the band limited signal from before, only it doesn't have those overlaps. And what really happens here is that we have one signal, and then we have other signals that actually masquerade as being the same signal, yeah, by basically happening to also be reconstructed by this box filter. And due to those other signals masquerading as the signal that we're interested in, that we want to reconstruct, we are having aliasing. And this is actually where the name aliasing comes from. Like there's a signal that masquerades as another signal, and therefore uses this other signal as an alias. So, and as for those limitations, like the signals that we're usually dealing with in computer graphics not being band limited, and therefore not exactly reconstructable, we just have to live with aliasing. So we have to somehow deal with aliasing, and this is actually regardless of the sampling rate. Like there's just no guarantee, no upper bound for the sampling rate that we know of that we can use to avoid aliasing. And so we have to develop strategies to avoid aliasing, and those strategies are like commonly referred to as anti-aliasing techniques. And there are actually a bunch of different anti-aliasing techniques. And what this basically centers around is sample placement. Like an obvious strategy is to just use more samples. And an obvious limitation of that is that we buy that at an increase in computation time. And there's also lots of other issues that come with just naively taking more samples. Like, for instance, we perform like a lot more operations, and they're usually floating point operations. And therefore, we also increase the potential for floating point precision issues and for rounding errors, etc. So, and what successful anti-aliasing strategies actually boil down to is an educated decision where to place samples. Let me give you an example, and the example here is actually one where I compute shadows in an image, and it just so happens that the human visual system, like perception theory, says that the human visual system is less sensitive to white noise than it is to uniform sampling patterns. And you can actually see that here in the way that I compute those shadows. Like here on this image, I generated this image by placing samples on this light source and thereby generating shadows. And as you can see, like here on the left-hand side, I'm using this uniform sampling pattern to sample the light source. And on the right-hand side, I'm using the exact same number of samples in order to sample the light source, but here I'm using white noise. Here I'm just using white noise distributed over the area of the light source. And with the exact same number of samples, you can already see that the result is visually much more pleasing. Like when you zoom into those regions, then you can, for instance, like you see those very prominent artifacts here on the walls. And here on the right-hand side, where I use this jittered random sampling pattern with white noise, you can see that the shadow on the wall actually looks kind of convincing. And you can also see those differences here in the penumbra of the soft shadows, where the uniform sampling patterns and those banding artifacts actually look quite distracting to the human eye, while the soft shadows that I compute with a white noise pattern look almost pleasing, or almost the way they're supposed to look like. So, and the same thing is actually true when we perform anti-aliasing in image space. And the strategy here is that we just place samples, and we in the model that we're assuming here, pixels don't have an area, but they're just points. They are points on the image plane. And when we perform anti-aliasing, then we just place more points on the image plane, and we center those points around the actual pixel positions. Like, and then when we do so, we are basically sampling again, right? We're using all those infinitesimal points to sample the image plane. But now we're not using a Shah function anymore, but rather a function where the spacing between the individual deltas, between the spikes of the delta functions, are potentially non-uniform. Like we'll now make like an arbitrary decision about that spacing, about the gaps between the spikes of the what was formerly the Shah function. So then in the end, after we sampled the image plane, we again use some type of reconstruction filter in order to combine the various samples that we have taken. Like here's an example of what that looks like. And the function that defines those gaps, those spacings between the individual spikes, is just a random function. Like the image plane is given as pixels, and we're just sampling around the center of each pixel, like around each pixel position. And we're just using a uniformly distributed random offset for the various sampling positions. And in this very case, we decided to use 3 samples per pixel. And this jittered sampling pattern actually has like a bunch of issues. And the issues being that that the samples for the individual pixels actually form clusters. And On the other hand, we have certain other regions of the image plane that are actually undersampled. So this is actually an issue because this results in decreased efficiency of our sampling pattern, and we're generally after sampling patterns that are that are kind of pleasing, like in regards to the white noise sampling pattern that we saw before. And on the other hand, we also want a sampling pattern that is efficient, and we will, like in a little bit, we will discuss discrepancy as a measure of efficiency of our sample placement. But what we already can see here is that clustering and undersampling determine how efficient our sampling pattern actually is. And there are several ways to make our sampling patterns more efficient to avoid clustering, and one such approach is called stratification. And stratification really sees us to subdivide our domain, like our individual pixels here, into like a couple of tiles, and those tiles they are called strata. And then we don't just like randomly place samples inside the pixel itself, but we place one sample per stratum. And like this will usually result in a better distribution of our samples. Like samples can still cluster, but we are mitigating this by introducing the strata. Like this sample here, for instance, will never be able to move up towards that sample up here, right? But in fact, stratification has several issues, and one of the biggest issue here is scalability. Like when we were to add more strata, like the next step would be that we just subdivide each of those tiles into four other tiles. And we are actually quite restricted to how many strata we actually end up with when we do this. Like we'll by that we would have to increase the number of strata by 4. And like we cannot just say, okay, we want to add one more sample. Like we always have to make the decision that we place, like in this case, 4 more samples per stratum. And this, of course, doesn't scale very well when we're going to higher dimensions. And then another issue actually has to do with higher dimensions. Like those stratification patterns only work for a fixed number of dimensions. And as a matter of fact, like we will later talk about ray tracing, and this is actually a whole family of algorithm, and one member of this family is the path tracing algorithm, and it's actually one of the most widely used algorithms to compute global illumination and photorealistic imagery. And there you compute integrals over functions that have a potentially an infinite number of dimensions. Stratification is just not very well suited to that. So earlier, I already said that the efficiency of the sample placement that we're using is described by something that is called the discrepancy. And the discrepancy is a measure of efficiency, and we want to minimize the discrepancy. And like very informally speaking, like when we have our sampling pattern, then we compute those bounding boxes around the samples. Like we can compute those bounding boxes around the samples, and what we want to reduce, want to minimize, is the overlap of those bounding boxes. Like, and you can already see, like there is a pattern that would minimize the overlap here, right? And this would just be a uniform pattern. If we were to choose a uniform pattern, that uniform pattern would actually minimize the overlap of the bounding boxes. And so there are like different competing objectives here. And so on the one hand, we want to reduce the discrepancy, which is somehow tied to the overlap of those boxes. And on the other hand, we want to avoid uniform sampling patterns. Like we want to have sampling patterns that are like, for instance, white noise, and there are other types of noises and other types of kind of random patterns. And we want to have a relatively random pattern, and at the same time, we want to minimize discrepancy. So discrepancy, what does it really mean? And for that, we just consider a family of polyeder, and a family of polyeder that is defined for n dimensions. and that is centered at the origin, and whose support or whose edge length is less than 1. And like in 1D, this would be a line of that would range from 0 to somewhere below 1, and in 2 dimensions this would be a rectangle like we saw earlier, and in 3 dimensions we would have boxes, and they are centered at the origin and have an edge length that is less than 1. And then we consider a set P of n sample points inside the polyeder, right? And the discrepancy of P of this set of points with respect to the polyeder B is just this: is the supremum with regards to each element in the family of polyeders B in the family of polyeders, and then the absolute value of the number of samples inside that polyeder over the number of samples in the set minus the volume of the polyeder. And the volume defined as an n-dimensional function, like in 2 dimensions, it would just be the area of the polyeder. And here's just a quick example of how we would compute this, demonstrated using a bunch of different polyeder. Like suppose we have this tile, like this region of image space here, and then we compute the discrepancy by just enumerating like a bunch of polyeders. And let us start with this polyeder here, like with the polyeder that ranges from 0 to 0.9 in the two x and y directions. And then we would compute the volume, which in 2D is just the area of that region, and that would be 0.81. And then we would compute the discrepancy by just counting the samples inside that polyeder and dividing that by the number of samples overall. And then we would subtract from that the volume, and we will find out that the discrepancy with respect to this polyeder is 0.19, right? So then we would do this for the next polyeder, like this polyeder here from 0 to 0.6, for example. And then we would compute the discrepancy for that, and we would maybe find out that that discrepancy is 0.14. And then we would do this like for more polyeders, and like in fact we would do this for all possible polyeders. Right? We would just enumerate all possible polyeders, and then in the end we would just take the maximum of them as the supremum. And here, we just computed the supremum with respect to this set of polyeders B1, B2, B3. And this would give us the overall discrepancy with respect to this family of, or this set of polyeders. And our aim is to find functions that minimize the discrepancy. Now, so you already have an intuition for that the discrepancy is a measure that relates the number of samples to the volume of those polyeders. Yeah, like by testing all those all possible polyeders, we can basically rule out outliers. Like if there are certain samples that are outliers, then those outliers would define the supremum of the set of this set of points, and therefore we would identify that that the discrepancy is relatively high. So and here's basically that same example again, just with maybe with a bit of a nicer presentation and on a single slide. And like I'm again having this bunch of polyeders, and I'm computing the discrepancy with respect to all possible polyeders as being the maximum discrepancy over all the polyeders. So now that we understand what discrepancy is, we already have a instrument at hand that helps us to assess the efficiency of a sampling pattern. And as a matter of fact, there's a whole research branch that is concerned with finding low discrepancy sequences that minimize the discrepancy. And like I said, there are opposing objectives here. As we, on the other hand, want the signal to expose some kind of randomness, And therefore, one type of low discrepancy sequences are so-called quasi-random numbers. Like, this is actually a very advanced topic, so I'm just dropping a few buzzwords here, and they are basically pointers that you can follow if you're interested in those. And like what those quasi-random numbers have in common is that they actually follow a uniform construction pattern, but they kind of look random, right? They look as if they're a random sequence, while in reality they aren't, and in reality they follow a uniform distribution pattern, but still they also minimize the discrepancy. And there are also actually other sequences that have a relatively low discrepancy, and one sequence that has become popular in the recent years is the blue noise pattern, and this is just another low discrepancy pattern that that I'm just dropping here as a buzzword. And if you are interested in that, you can just follow it by looking up what that implies. So, and apart from those patterns that try to approximate randomness, there are also certain uniform patterns that are used and that are replicated for all pixels. And those are like by the vendors. They are implemented as part of the GPU rasterization pipelines, and they are just fixed patterns that are used for each and every pixel, like as opposed to the quasi-random numbers or the jitter sampling patterns that we saw before, that provide sampling patterns with generally different sampling positions and non-uniform sampling positions for the whole image plane. Those sampling patterns are fixed with respect to what happens for a single pixel, and those are just like a bunch of sample patterns that I just picked out, and they are what AMD implemented like 10 years ago, and where I found documentation for. And this is what the vendors call multisample anti-aliasing. As you can see, that actually works quite well. Like, here's an example where I use either of those four multisampling anti-aliasing pattern that I've been showing you before. And here's a zoomed in version of the respective patterns, and you can see how sampling and reconstruction with those patterns like relatively effectively is able to reduce aliasing. Like, you can still see aliasing, and you can also see how aliasing improves with a wider filter, like with a sampling pattern that places more sample per individual pixel. And like, you can see this here in this region where with the 2x oversampling you can still see some very significant aliasing, whereas with the sampling patterns, like with the 8x sampling patterns, this is almost completely gone. So when we talked about sources of aliasing earlier, we also said that texture sampling can be a source of severe aliasing, and you can see this in action here actually. Like, what I'm doing here is I'm sampling the texture here with the same sampling rate that I'm also using to convert the polygons in the scene that I'm using to produce the raster image. And that's not necessarily a good idea, in particular when you have textures which have high frequencies in them, and then you map them to polygons that are far away. And then the decision which ones of the high frequencies to assign to the fragments that you're currently rendering is kind of arbitrary, yeah? Because you're just picking one of those frequencies, and the variability in the texture is so high, and you cannot really make an educated decision. And you can, like in the texture here below, I actually performed oversampling to reduce the effect of this. And you can see that even at a distance, this isn't even very successful. And there's a built-in mechanism that GPUs support in order to mitigate texture aliasing quite a bit. And this approach is called MIP mapping. And the idea is basically to store the texture image not only at a single resolution, like this is the full resolution texture image, but to also store downsampled versions of the texture image. And by downsampling the texture image, basically removing high frequencies from the texture image. Right? When I downsample the image, I'm using variability in the image, and I'm basically reducing the frequencies. So and then I can devote to different distances in the image, like depending on how far away the samples are that I'm taking, I can devote different levels of this so-called mipmap pyramid. Right, and features that are farther away, I would map those low frequency textures to, so in order to avoid that problem that I showed you earlier. So then the question remains how to choose the actual MIP levels, and we're doing this on a per fragment basis, right? And when we're rendering our raster points, we have associated with the raster points, we have like several fragments, and those fragments have associated with them depth values. So, and in order to choose a MIP level, we do this with respect to the neighboring fragments and with respect to the neighboring raster points. And therefore, we just take the slope into account of neighboring raster points. Like when we decide for MIP level, then we compute the slope with respect to the neighbor, and that tells us which MIP level to use. So, and in order to compute derivatives, a fragment needs to have some knowledge about its neighbors. And the way we so what we learned about scan conversion before is that we basically handle each fragment individually. And as a matter of fact, this is not true on GPUs, but for this very reason that we need to be able to compute derivatives, GPUs actually process fragments in groups of 2 by 2, and they are graphics people just call them quads or fragment quads. And across those 2 by 2 quads, we have first order derivatives available. First order partial derivatives in both the x and the y direction. And those partial derivatives we can actually use in shader programs that allow us to program with code that directly runs on the GPU. And in those shader programs, we have the slopes and the first order derivatives of those quads available, and we can query them, and we can also use them to choose MIP levels for texture lookups. So, and with that, we're finishing our discussion about sampling, and we can finally go over to discuss our free rendering algorithms. Like today, I'll not start discussing any of the individual algorithms, but I'll just present like an overview of the few algorithms and provide some detail on how they actually differ. Like the reason why I chose those exact three algorithms is, in the first place, is relevance. Like the algorithms that I'm choosing, on the one hand, we're discussing the rasterization algorithm, and the rasterization algorithm is basically just what GPU vendors implement. Like this is the algorithm that is implemented on GPUs. We will then also discuss deferred shading, and deferred shading is a algorithm that is kind of relevant to the gaming industry, actually. Like in the gaming industry, there's quite often game engines use a variant of the deferred shading algorithm. So this is also a very relevant algorithm, but an algorithm that might be relevant to another industry than to the industry where the simple rasterization algorithm is relevant. While, as a matter of fact, the deferred shading algorithm is actually an extension to the rasterization algorithm. And then we will also discuss ray tracing, and we're discussing ray tracing for several purposes. We're discussing ray tracing for the fact that ray tracing has gained quite a lot of popularity in the last 10 years, because it's an algorithm that is easily implemented on GPU, and it has very much parallelism. And then on the other hand, we will also discuss ray tracing because very recently, like 3 years ago, NVIDIA started selling GPUs that actually can do ray tracing in hardware. And the rasterization algorithm is the very first algorithm that we will discuss, and we will discuss it so that we can later understand the fixed function pipeline of GPUs, like the pipeline that was traditionally implemented by GPUs when the first GPUs came out. And then we will discuss the G-buffer or deferred shading, deferred lighting family of algorithms, and this algorithm being an extension to the rasterization algorithm, what it supports is actually rendering with many lights. And we will also, when we discuss the rasterization algorithm, we will discuss why the ordinary rasterization algorithm isn't very efficient in the presence of many lights. And then we will discuss ray tracing as more of a physically based approach that is quite different from the two rasterization-based algorithms, but it is interesting nevertheless. So there's one remark about when we discuss those algorithms, we will make comparisons about those algorithms in terms of, like, we will try to assess the complexity of those algorithms. And when we do so, we should note in the first place that there are no algorithms that are like fast or slow per construction. But it's important to note that depending on the type of phenomenon that you are interested in, you have to choose the right algorithm. Like, for instance, when you know that you have very few point light sources, then you might choose a different algorithm than when you know that you have many lights, or even when you know that you have light that can arbitrarily bounce throughout the scene and global illumination is important to you. So there are not algorithms that are slow by construction. So the algorithms that we will consider are generally efficient algorithms. Like what those algorithms are designed to solve, the problems that they are designed to solve, the algorithms are actually efficient at that. Nevertheless, the frame rates that can be achieved with the algorithms might actually differ quite a lot. So in some of the algorithms that we will discuss in the light of efficient hardware implementations that are out there. And this is especially true for the rasterization algorithm and for the ray tracing algorithm. And it is worth noting that the choice of algorithms that are made also depends on that those algorithms are actually implemented in hardware. So in our approach will be that we will devise formal descriptions of the free rendering algorithms. And based on that, we will analyze their complexity. And we will do this for sequential versions of the algorithms, and we will do it for versions that can run on a PRAM and that will be formulated in terms of the work time per rating. And for that, we will take certain input into account, like all the algorithms are subjected to input like polygons to a certain image resolution that we're rendering for and a certain number of light sources. And in the next session, we will begin by doing so for the rasterization algorithm. And I hope that you tune in then. See you then.